Welcome to the Professor's DuBois channel. This is Professor Corey, and this video is a mini lecture based on our fourth lecture covering material from Chapter 5. So the idea here is I'm just trying to get, the big items in just a short amount of time so you can have a resource to review the material. So please come to the actual lecture where we cover this material much more slowly, with more examples and more practice problems. So let's just get started here. We're going to go into heat transfer from a chemical reaction. And this is new because we've talked about heat transfer between two objects. We've heated a piece of metal and put it into water, and we said that the heat lost by the metal was equal to the heat gained by the water. We like to use the equation heat lost plus heat gained equals 0. It's just a preference, personal preference. And in this case, we can use a delta H of the reaction plus MC delta T equal to 0. So we're going to show you an example of that. And we are going to solve in this problem, we're going to solve for the delta H of a reaction. And this reaction is zinc reacting with HCl. So I wrote the reaction down below. We're going to make zinc chloride and hydrogen gas. So the formation of that gas lets us know that this is actually a chemical reaction. Remember, we have drivers for chemical reactions: gas forming, form a precipitate, form water. So we indeed have a chemical reaction going on, which may be endothermic or exothermic. So what we're going to do is we're going to use the delta H reaction plus MC delta T of the solution. So the solution is the zinc and the HCl. We're going to have to add those two masses together. We're using 4.184 as the specific heat of the solution, and we're doing the delta T, final minus initial, as always. So when we cancel our units while solving this, we end up with joules. So I can move the value 1710 to the other side of the equation, get the delta H reaction by itself, and it feels like I'm done, right? I've got 1710 joules, but looking back at this problem, what we're looking for is kilojoules per mole. Okay, simple enough. I'd probably do the kilojoules conversion first. I would be in, just joules to kilojoules. Know that conversion for this test, very common. But what I have to do is get the per mole, and this is per mole of zinc. So real common to want to know on a per mole basis or a per gram basis. So if we added more zinc, we would have more energy being given off. This one did have a negative value, so it was indeed an exothermic reaction. So we have to set that to an amount so that we could do some calculations with that. Another type that's very, very similar is a dissolution. And a dissolution is like dissolving. In this case, we're dissolving lithium chloride. This isn't a chemical reaction. We don't have those drivers. And if you look down on the bottom left here, I wrote this as a reaction. This is, you might see something like this in a textbook. So we've got the lithium chloride, the solid, going to the aqueous lithium chloride. And if you remember, when we were doing net ionic equations, if we had a soluble ionic compound, we would write the ions here. We'd break it apart, and we'd have the ions both with the aqueous symbol. And what's really happening here is the waters are surrounding these ions. So in this case, I've just drawn like 3 waters around this chloride ion, and there may be more than that. But what's important to realize is when these water molecules surround these ions, there's actually forces of attraction there that release energy. So if this is a great amount of energy released, this might be an exothermic reaction. But the other thing we have to consider was how much energy was required to break all those bonds of the solid lithium chloride. So there's really 2 parts to consider here, and we'll let the data or the result, the delta H value, tell us which was more. So delta H dis plus MC delta T of the solution. Again, I'm going to add the 2 masses, 4.184 for the specific heat. A little bit tricky here with the temperatures. They said a temperature decrease of 5.8. Well, that's my delta T, and it went down. So I write that in, minus 5.8. I can solve. I end up with units of joules, move it to the other side. This is going to be a positive value. This is going to be endothermic. So this tells me that it took more energy. More energy was required to break this solid apart than what was released when the ions were hydrated. So again, we're in joules, which, that's the amount of energy for this particular situation, the 24.7 grams. So I can divide by the 24.7 grams and get a joule per gram. So this is kind of useful. We could use this, I would know how much energy would be required for 10 grams or 30 grams using this factor. So we can do some manipulations of these equations, and there's really only two things that happen. One thing we can do is we can write a reaction in the reverse direction, and I like to use this word flipped, and I'm not sure if that's really perfect or not. But see, in number one, our reactants are the CH4 and the 2O2. Well, in number two, the products are CH4 and 2O2. So all I've done is switched my reactants and products. It's kind of like, maybe you could call it the reverse reaction. Well, the result of that is simply changing the sign of the delta H reaction value. So if number one was negative 802, then number two, I flipped it, the delta H reaction, same magnitude, different sign, positive 802 kilojoules. The other thing we can do is we can scale a reaction. So in this case, I'm taking this reaction. I have a delta H, negative 802, same as before, and I can multiply everything by a half. So I would have 1/2 CH4 plus 1O2 going to 1/2 CO2 and 1 water. This is fine. I have to do the same thing to that value. So I have to take half of that 802. Sign doesn't change, just the amount. So if I were to multiply everything by 2, I would have to multiply the delta H reaction by 2. So those are the two things we can do. We can flip a reaction, changes the sign, or we can multiply by a number or a fraction, and this is fine as well, as long as we do it to every one of the compound's elements and that delta H reaction. Just something to point out, as good a time as any, is this enthalpy, or the delta H, really depends on the states. This is really important. So it's important to write your states and just be aware of the states. And a good example here is this reaction that looks pretty similar, but notice one of them produces water in the gas form and the other one's in the liquid form, and these have different delta H values. So be aware of that. This is just showing how I'm going to take a reaction, water in the gas phase going to hydrogen and oxygen. I have a delta H. If I flip it, I made the products now the reactants. The P up there I just wrote for products. Now those are the reactants, and the previous reactant is now the product. It's like the reverse or the flipped, so I changed the sign, and now I'm going to multiply everything by 2. I've got 2H2 plus O2 going to 2H2O. So I have to multiply the delta H by 2 as well. So negative 241.8 times 2 gives me the negative 483.6. That's units kilojoules per mole for this reaction, for the reaction as written. So it's good practice being able to manipulate these reactions. You're going to see in the next lecture we're going to do some more of this. So until then, I just be familiar with the two things that we can do. We can flip the reactions, change the sign. We can multiply by a multiple as long as we do it to everything. And of course, we need to be able to solve for the delta H of a dissolution or the delta H of a reaction, what we did earlier in this lecture. So thanks for watching. Please give the video a thumbs up and subscribe if you'd like to see more mini lectures on the Professor DuBois channel.